Alright, so for 3b we're finding another power series representation for a function, and this time we're trying to find the integral of arctan of x squared. The antiderivative of that. This is something that would be pretty tough to do using integration techniques. So this is a good example of why you want to use Taylor series in math, because it makes functions that are otherwise difficult to integrate pretty easy because you can just turn them into polynomials. So recall, for this one, you need to know the power series representation of arctan of x. So the power series representation of arctan is, we're going to start, we have odd powers of x. First we should say it's going to be alternating. We have odd powers of x, and we divide by that same odd number every time. So you can see here that when you plug in n equals 0, you get the term x, which is the first term of arctan. Next you get negative x cubed over 3, on and on and on. Okay, so that's arctan of x. So if we want to find the integral of arctan of x squared, first we need the series for arctan of x squared. So arctan of x squared, and remember that the interval of convergence for the arctan series is negative 1 to 1 in brackets. You can include the endpoints. So arctan of x squared is just going to be substituting x squared everywhere there was an x. So that series, n equals infinity, or n equals 0 to infinity, negative 1 to the n. So instead of x, we're going to have x squared raised to the 2n plus 1 over 2n plus 1. That can be simplified a little bit. We have negative 1 to the n. When we have x to the 2 and then that raised to the 2n plus 1, remember we can take the product of those two exponents. So this is going to give us x to the 4n plus 2 all over 2n plus 1. Alright, so this is our series now for arctan of x squared, and we want to do the antiderivative of that. Again, doing this antiderivative by using integration techniques would be tough, but taking the antiderivative of this series is pretty simple. So we have n equals 0 to infinity, and let's think about what we're going to have here. When we take the antiderivative of this, everything that's not the x is a constant. So negative 1 to the n stays there. When we get to the x, and there's going to be a 2n plus 1 on the bottom that stays there. Constant terms. When we do the antiderivative of x to a power, remember you raise the power by 1 and then divide by that. So we're going to have x to the 4n plus 3 if we add 1 to 4n plus 2. And you have to divide by that new power as well. So all we did was take our series here and take the antiderivative of it. When you take the antiderivative, you're never going to have to worry about changing your n value, because all the changes that occur bump it up higher, which is just going to show in these powers of things. So all we had to do here was take the antiderivative of that. Remember that x is your variable. You're going to hold all the n's constant. And remember also that your interval is the same as it was before on the interval negative 1 to 1, including both endpoints. The reason in this case that our interval stays from negative 1 to 1, even though we plugged in something for x, is how I'm going to show you that here. So in our original arctan formula, this means x has to be in between negative 1 and 1. When we plugged in x squared instead of x in this arctangent formula, what we're implying here is that now x squared is in between negative 1 and 1, because that's our new argument of the function. But if x squared is in between negative 1 and 1, First of all, it can't go that low anyway because it can only be as small as 0. But if x squared is in this range, that implies that x is also in that range. Because the only way you could get the x squared to stop at 1 is that if x was in between -1 and 1. So I just want to point out that in the case that whatever you plugged in for x, you know, say it had a coefficient on it, that would change your radius of, or that would change your interval and your radius of convergence. However, changing x to x squared inherently doesn't if you already had -1 to 1 as your interval of convergence. So this is still correct here. So let me just give you a quick example. If we had done arctan of 2x instead, we would have taken our arctan formula. Everywhere there's an x, we would have plugged in 2x. And then if we wanted to find the interval, we would have said that 2x has to be in between -1 and 1. Because this formula says whatever x is has to be in between -1 and 1. Now our x is 2x. So that means here x actually has to be in between -1/2 to 1/2. So the series formula for this you can get by plugging in 2x for x, but its interval of convergence would be -1/2 to 1/2, not -1 to 1.